Welcome to this video in which we introduce the concepts of internal forces in a beam. These forces are tension, shear force, and bending moments. The idea behind internal forces is that they are forces that are typically internal to an object like a beam. And beams are long, narrow pieces of stuff, typically steel or other construction materials. And the reason we care about this is that beams are what we often build structures out of, and internal forces are the things that determine whether or not the beam fails under certain loading conditions. So let's define these forces, or at least describe them. We have tension, and tension is a force along the axis. So I have a beam here. This is a two-dimensional representation of a beam. The axis is the long, direction of the beam, and so tension will either stretch the beam like this or perhaps compress it. Okay, shear force if I have a beam and there's a shear force, that means that there is a force. Actually, we need to push this into the material. There's forces in the materials pushing part of it one direction and part of it the other direction. So you can think conceptually of the way scissors cut things. In fact, scissors are often called shears. Scissors cut things by applying shear forces to the things they cut. So you've got one blade pushing down, one blade pushing up. And so shear force essentially means that the beam gets cut in half if you've got something that fails due to shear force. Bending moments and the idea here is that these are moments that cause bending. So if I have a beam that should be straight and ends up looking like this because maybe, I don't know, I've dropped a very large box on it or something like that, this box is applying a moment which causes the beam to bend. Okay, so it's causing this end on the right to curl up and this end on the left to curl up. So that's sort of an introduction to these internal forces. The way that we find internal forces is we take a beam, and this beam may actually be loaded in several different ways. I might have a particularly heavy thing here. I might have another support here. I can have all sorts of different loading, but the idea is we take the beam, and at some point where we want to understand these internal forces, we make a cross-section through the beam. So in this case, I'll call it cross-section AA, and we split the beam into two components, at least conceptually. So I'd have this guy here. I'd have reaction forces here and an upward force here, and maybe a weight force that the beam itself represents. And then I'd have over here the other half of the beam, and I have an upward force here, and again I might have a weight force. And we identify two vectors and a couple. So we have a vector T. This is a tension force. We have a vector V. This is a shear force. And we have a couple M. And these are drawn, tension is always drawn away from the cut. V is drawn so that if V is a positive force, it will tend to produce a clockwise rotation. So here I have a V going down. That would produce a clockwise rotation of this end. Here I have V going up. It produces a clockwise rotation. And then M is drawn as if you think of this beam up here, or we'll draw some scary teeth in it, as a smile. If I'm looking at the right end of a beam, so if I'm over here, then I draw the bending moment up around it like this, so it looks like cheeks on a smile, basically, and the opposite direction if I'm on the left end. Okay. So the idea is to find these internal forces. And again, we want to know these internal forces because they tell us about internal forces are typically the things that cause failure in beams, causes it to either buckle or to bend or shear off, things like that. So that's why we want to know them. When you talk about internal forces, you need to be a little careful. When we've talked in the past about free body diagrams and we're assuming that we have completely rigid objects, we've talked about the idea that maybe gravity can be represented as just a force at the center of gravity of the object. But when you're looking for internal forces, you have to make very clear whether you have a concentrated force. So a concentrated force you might think of as an elephant wearing an ice skate standing on this beam. So the force, the weight of the elephant is applied at pretty much exactly one point, versus a distributed force. So gravity is a distributed force. If I have an elephant that's laying down on the beam and spread out everywhere possible, spread out as wide as possible, then that would be a distributed force as well. When we're doing free body diagrams of the interaction of the beam with its environment, it doesn't really matter how we represent these forces. But when we're looking at internal forces, the tension, shear force, and bending moments actually do matter how we represent the forces applied to the beam. Okay, so with that introduction, let's do a simple example. And suppose we have a beam that looks like this. At point A, it's attached, it's got a fixed attachment to a wall, and it's 10 feet long, and out at the edge of the beam I've got a 100-pound weight. So I don't know, this might be like holding a sign or something. I don't know. I'm sure you can come up with a better application than I can. We'll assume the beam is weightless and that, again, it's fixed at point A. And what we want to do is find the tension, shear force, and bending moment at these points AA and BA. Now to do this, we'll cut the beam at AA and BB. To do this, for example, at AA, we'll cut the beam at AA, get two free body diagrams, and then solve for the internal forces. But in order to do that, we need to know the reaction forces and the couple at A. So the first thing we'll do is a free body diagram of the entire beam. And with this free body diagram, then we will find the reaction forces. Okay, so our reaction force, we can have a vertical component, a horizontal component, and a moment. And then you can see if we sum the forces in the x direction, we have FAX. There are no other forces in the x direction, so the sum of the forces in the x direction is 0, which says that FAX is equal to 0. If we sum the forces in the y direction, we have, whoops, got a little carried away there. FAY minus 100 pounds, and that's equal to 0, which tells us then that FAY is 100 pounds. And finally, the moments we have, let's look at the moments about point A. We have MA minus 100 pounds. That's basically this force here. It's acting on a moment arm of 10 feet. And that's equal to 0, which tells us that MA is equal to 1,000 foot-pounds. Okay, so there you have it. We now know what the forces on the beam are. So let's find then the internal forces when we cut the beam at AA. Okay, we'll create ourselves a new window to draw here. We'll take our beam and we'll draw half of it here. Then we'll have the cut at AA and the rest of it. And we have our reaction forces. We know that this is 100 pounds up. There is no horizontal reaction force, and we know that the moment here is 1,000 foot-pounds. We know over here we've got 100 pounds down. And if I remember correctly, well, I don't think I've ever said, let's assume that AA is 8 feet out along the beam. So this is going to be a distance of 8 feet from this edge to this edge, and this is going to be a distance of 2 feet. Okay, let's draw our internal forces. We have tension. We have our shear force, and we have our moment, bending moment in this case, because it wants to cause the beam to bend. Okay, so let's go ahead and find, using first this free body diagram, let's find T, V, and M. Well, T, if we sum all of the forces in the x direction, the only force in the x direction is T, so that says T has to be equal to 0. If we sum the forces in the y direction, we have 100 pounds minus V is equal to 0, which says that V is equal to 100 pounds. Okay, and if we sum the moments, we have 1,000 foot-pounds plus M. Let's see, and then we also have V pushing down with a moment arm of 8 feet. So we'll have plus V times 8 feet, and this is equal to 0. And so V is 100, this is 100 pounds. So we have 1,000 foot-pounds, and I got the sign here wrong. I'm sorry. This force here is pushing in such a way to make the moment clockwise. And, okay, yeah, this is right. So I have 1,000 foot-pounds minus 800 foot-pounds is equal, M plus that is equal to 0. I can solve this and get M is equal to minus 200 foot-pounds. Okay, so that basically now gives us the internal forces. Again, the reason we care about this is we know now what the shear force is at this point where we've done the cut, and we know what the bending moment is. Okay, very quickly, because I'm out of time, if we look at this free body diagram, again, the sum of the forces in the x direction is 0. It says T is 0. The sum of the forces in the y direction is 0, which again tells us that V is 100 pounds. The sum of the moments is also 0, Here I've got a moment that's inducing clockwise rotation, so this will be a minus m. I then have the moment about this point that the 100-pound force is generating through a 2-foot moment arm, and that's counterclockwise, so I have 100 pounds times 2 feet, and this is equal to 0, which says that m is equal to minus 200 foot-pounds. So what we've shown here is how to find these forces, and it also turns out that it doesn't matter which free body diagram you use after you've made your cut. You'll get the same answer if you use the one on the left of the cut as you will get when you use the one on the right to the cut. So with that, we'll stop. Hopefully this has been a useful video.